Okay, so I'm going to be talking about whether the fastest stars in the Milky Way are on the run from another galaxy. Now, given I've titled my talk in the form of a question, you can probably guess I believe the answer to this question is yes. So my goal in this talk is trying to convince you the answer is yes, too. Start by thanking my collaborators on the work, Dennis Ercole, Robert Izzard, and my supervisor, Wyn Evans, who I'm sure was very glad that I found this deep in the internet. So I'm going to try and answer at least 5 questions today. What do I mean by fast star? How are fast stars made in the Milky Way? Where outside the Milky Way could they be coming from, if not the Milky Way? When will we know for sure whether or not I'm right? Why is this trivia? Why is this interesting? Because if you have a galaxy, there must be a fastest star in it. So why is it interesting that maybe they're coming from a different galaxy? And then I'm going to try and answer some of your questions at the end. So what do I mean by fast star? We're used to thinking of stars and galaxies as stationary, movable objects. But actually, they really aren't. Galaxies rotate, even our own Milky Way, at 250 kilometers per second. Looking at this graphic, you might think that stars move around with the galaxy, they rotate with it, like a solid object. But that's not true. Even within a galaxy, stars orbit around different ways, in circular orbits, in elliptical orbits, and sometimes in very elliptical orbits. And so if you want to understand how stars move in a galaxy, you really need to study a very large number of them. So enter the European Space Agency's Gaia Space Telescope. This was launched in 2013 and is conducting a 10-year mission to measure the positions, velocities, and distances to over 1 billion stars in the Milky Way. So we know there's about 100 billion stars in our galaxy. So that's still a very small percentage, but it's covering quite a large volume. And the way it's going to do that is by rotating round, so it's scanning across the sky, and then tumbling, so it's scanning along the sky, so that over its 10-year mission, it can build up a map of the entire night sky. So it's going to look at every single star, every single one of these 1 billion stars, 70 times over these 10 years. And by measuring where a star is on different observations, it can measure its position, its velocity across the sky, and it can also measure the distance to the star through an effect called parallax. So if you're walking past a tall building, you can see that building moving against the clouds in the sky. And that effect is called parallax. And by measuring that, you can work out the distance between you and that building. So that's how it's going to work out the positions, velocities, and distances to these billion stars. So if you have the positions and the velocities of a large number of stars, you can work out how the night sky is going to change over the next few million years. So the European Space Agency released a first preliminary data release last year for the brightest 2 million stars. So nowhere near the full billion, just the brightest 2 million. And the reason it being preliminary means that there are lots of straight lines and gaps in the data. So that's why it looks like that. But then if I play it, you can see that stars are actually moving quite a lot on the sky over these time periods. I mean, they're not human survivable time periods, but yeah, so the sky will entirely change. The sky is very dynamic. And you can see that stars are moving around essentially randomly, except for these 2 stars here, you may be able to see, are moving together. That's because these 2 stars were born together. And so they've been traveling together for the last few billion years. Now, if you have a list of all the stars in the night sky and how fast they're traveling, you can sort that list and find the fastest stars. And you might want to do that because that's just interesting. But if you do that in these first 2 million, you don't get anywhere close to the sort of velocities that we know about for the very fastest stars. The very fastest stars are the hypervelocity stars. And the other name for these stars is more enlightening. It's the unbound stars. These stars are traveling so fast that they're not bound by the gravity of our galaxy to stay in the galaxy. So they're not orbiting around the galaxy. They're traveling a straight line out of the galaxy. So they're going to travel away from our galaxy. We know of about 24 hypervelocity stars. Most of them are very massive, about 3 times heavier than the sun. And that means they're very bright and blue. I'll get back to why that's important in a second. And they're between 50 to 120 kiloparsecs away. To give you a sense of scale, the sun is 8 kiloparsecs away from the center of our galaxy. 8. And the Milky Way is 700 kiloparsecs away from Andromeda, which is the other big spiral galaxy in our local group of galaxies. So comparing 8 to this range to 700, these stars are really on the very outskirts of what you might call the Milky Way. Now, the biggest uncertainty about these stars is that we have no idea where they're coming from. And I'm really going to hammer on that point in the rest of this talk. So to give you some background about stars, And why it's important these stars are blue. Blue stars live short lives. So this is a diagram showing the different types of stars we know about. And we classify them from M types to O types. So you can see there's a progression of size, just physical size. There's also a progression of color, going from red to blue. That's because these stars are different temperatures. So the reddest, smallest stars are cool, and the biggest, bluest stars are very hot. So if you look at a candle flame, the outskirts of the flame are red, and then orange, yellow, white, and then it was hot enough blue. So these stars are tens of thousands of degrees Celsius. These are a few thousand. But the other thing that goes with this scaling is the age. So M-type dwarf stars will live for 560 billion years. Now, the age of the universe is currently 13 billion years. So all of the M-type small stars are still in their infancy. Whereas O-type stars only live for 10 million years, which, while a long time, is really short on astronomical scales. The stars like the Sun live for 10 billion years, so the Sun's about halfway through its lifetime. And the hypervelocity stars are blue B-type stars, so they live for about 300 million years. Now, that seems large compared to O-type stars, but it's still quite a small time. This is about how long it takes the Sun to orbit round the Milky Way once. So over 300 million years, you really can't travel very far through space. And so if we're seeing these B-type stars way out in the outskirts of the Milky Way, far from where we know stars form, because stars form in the centers of galaxies, then we know they must have traveled fast to get to where they are now. So even before you've measured their velocity, you know they must have a high velocity in order to have gotten that far away from the center of the Milky Way. Okay, so hopefully you can see the gray region here. So you can use this to find hypervelocity stars. So you take a large survey of the night sky. The Hypervelocity Star Survey used the Slow and Digital Sky Survey. And on this plot, which is a map of the night sky, in the gray region is the region that this survey searched. So you can assume that we've seen all the stars out to quite far away in this gray region. Now, the reason it's a weird shape is because astronomers use a couple of different ways of mapping stars, coordinate systems. There is the equatorial system, where you just take the longitude and latitudes of Earth and just project them out onto the night sky. So the equator of your equatorial system is the equator of Earth. And that is the coordinate system which Slow and Digital Sky Survey used. So they searched the northern hemisphere in that system. But if you're talking about something in galactic scale, you want to use a system which makes more sense. So you make the galactic plane, because the Sun is in the disk of the Milky Way, you make that plane your equator. So you've turned to your coordinate system, and that's why you get this yin-yang type shape. So you've taken something which originally filled this top half and rotated it round. So from this survey of lots of stars, you pick out all the ones that are blue and faint. Blue, so they must be young. Faint, so they must be very far away. You then measure their velocity and write a press release. So they found about 20 of them. And you can see that compared to this large region that was searched, they're very clumped in one part of the sky. And that's the reason we don't really understand these stars at all, because there's no way to make fast stars in the Milky Way that can explain this clumping. So how are fast stars made in the Milky Way? This star here is a very famous fast-moving star in the Milky Way called Kappa Cassiopeiae. And it's traveling in this direction. And this red feature is called the Bullshot nebula. And it's created by the ionizing radiation from the central star acting like a snowplow on the gas and dust that lies between stars and piling up ahead of the star, and forming this very massive feature. And the distance between this star and this nebula is the same as the distance between the Sun and Alpha Centauri. So these are really massive features. So the key to understanding how fast stars are made is that many stars are in pairs called binary stars. And they can be different sizes, and they orbit around their center of mass. So they're not stationary either. And this orbit around their companion can be very, very fast. It can be hundreds of kilometers per second. And so if you imagine an object the mass of a star moving past the companion at hundreds of kilometers per second, there's a lot of energy bound up there. And so if you can somehow free one of these stars from their companion, you can release that energy and turn that into forward motion so you can produce a star that's moving fast relative to the galaxy. So there are three main ways to make fast-moving stars. The first is the binary supernova scenario. You start with a massive binary star in a close, rapid orbit. The more massive star then reaches the end of its life and explodes in a supernova. That frees its companion from the other star's gravity, and so it can fly away. And that can be up to 1,000 kilometers per second. The other scenario is a dynamical ejection scenario. This is where you have two binary stars coming too close in the center of a star cluster. For a series of chaotic exchange interactions, the two most massive stars end up bound into a binary, and the other two stars are kicked away at very high speed. And this again can be up to 1,000 kilometers per second. But the problem with this scenario and this scenario is that they can't produce fast enough stars often enough to explain the numbers of hypervelocity stars we've found. So that means you need a different mechanism. So we turn to the Hills mechanism, commonly thought to explain all types of stars, because it's the only one that can produce fast-moving stars fast enough, often enough in the Milky Way. So this is where a binary star passes very close to the massive black hole, which resides at the center of the Milky Way. So in case you didn't know, there's a 4 million solar mass black hole at the very center of a galaxy called Sagittarius A star. Now, when the binary is at closest approach to this black hole, it gets ripped apart, and one of the stars gets slingshot away at thousands of kilometers per second. So this definitely could produce fast-moving stars often enough to explain the hypervelocity stars. But the problem is that it should be kicking stars away in pretty much every direction. And so you'd expect to see hypervelocity stars all over the sky, versus us currently observing them in just one part. So this can't explain it. So I've just argued that there's only one way to produce stars fast enough, often enough in the Milky Way, and that it can't explain the clumping of the hypervelocity stars. So therefore, the hypervelocity stars cannot be coming from the Milky Way, or at least most of them can't. Right. So where outside the Milky Way could they be coming from? So if you were on a hilltop in Chile, in the southern hemisphere at night, you could see this. This is the arc of the Milky Way stretching across the entire sky. And if you know the hypervelocity stars can't come from here, then you might go to the next biggest clumping of stars in the night sky, which is here, which is just a smudge in this image. But it's the Large Magellanic Cloud. It's another galaxy flying past our galaxy, and really quite close. It's 50 kiloparsecs away. So it's only 5 times further away from us than the center of our own galaxy. And it's actually really massive. It's 10% the mass of the Milky Way. So it's smaller than the Milky Way, but still quite substantial. And why you might think how stars are coming from here is that it's aligned with where we see the hypervelocity stars. So we've looked for hypervelocity stars in this grey region. We found these red hypervelocity stars here. The LMC is now here, but its orbit over the past 2 billion years has followed this path across the sky. And so if you project this forward, you can see that it might end up in the region where we see the hypervelocity stars today. So maybe these are stars that are traveling ahead of the Large Magellanic Cloud. So what's the context for that? So firstly, as I said, the Large Magellanic Cloud is 50 kiloparsecs away. And remember, the hypervelocity stars are between 50 and 120 kiloparsecs away. So it's at the right distance scale for where we see these stars. Large Magellanic Cloud is also forming a lot of stars. In the Milky Way, one sun's mass of star is formed per year. So that's not the Milky Way forming a sun every year. That's an average rate. So it might form some smaller mass stars, and then every few years form a really massive star. But the LMC forms stars at a fifth of that rate, which is smaller, but it's not insubstantial. And that's important because we're talking about young, fast-moving stars. And the number of those that are produced is going to be proportional to the number of young stars that are being produced. But most importantly, the LMC is moving at 378 kilometers per second past our galaxy. Now, the speed that you'd need to be unbound from the Milky Way, as far out as the LMC is 450 kilometers per second. And so the LMC itself is almost a hypervelocity galaxy. So we don't actually know for certain whether or not the LMC is flying past our galaxy or whether it's orbiting it. So if a star can be ejected from the Large Magellanic Cloud, in the direction the Large Magellanic Cloud is moving, those velocities will add, and you can produce a very fast-moving star, which will be above the escape speed from that location. So you'll produce a hypervelocity star. So focusing on that idea, because this is the key idea of the talk, think of ejecting stars from a galaxy as like a cannon that fires in a random direction. if that cannon is mounted on a train, and the station observer would say that the fastest cannonballs are those that are ejected in the direction of the train's motion. So, like this. Analogously, the fastest stars are going to be those that are ejected from the valency in its direction of travel. So, what could be ejecting stars from the valency? I've talked about 3 mechanisms during the talk. The first 2 will definitely be happening. The binary supernova scenario only requires the LMCs forming stars, which it is. The dynamical ejection scenario only requires the LMCs forming stars in star clusters. But that's pretty ubiquitous. We see star clusters everywhere. So that's also true. But if we want the Hill's mechanism to work, to be producing very, very fast-moving stars, we need the LMC to have a massive black hole at the center. Now, at present, we don't know. Let's say we have ruled out a massive black hole at the center of this galaxy. We just haven't probed deep enough yet. So currently, the upper limit on the mass of a massive black hole in the Large Magellanic Cloud is 10 million solar masses. And the Milky Way hosts a massive black hole that's 4 million solar masses. And you'd expect a lower mass galaxy to have a lower mass black hole. And so we've not even probed below the Milky Way's black hole's mass. So we can't even say anything about this black hole or about whether it exists. So we can definitely pretend that there's one for now. So all of these could be operating in the LMC. So this is the only slide in this talk where I've actually done any work. The rest of it was just speculation. So you create, if you want to simulate runaway stars escaping a massive galaxy, you create single and binary stars at a star formation rate of the LMC in simulation. You simulate the binaries to see if any of them produce runaway stars. You take the runaway stars, eject them in a model of the LMC flying past the Milky Way to see where they end up at present day. But then you also follow the runaway stars to see if any of them reach the end of their life mid-flight and explode themselves as supernova. So there, what I'm talking about is you have a binary star. The first one explodes in a supernova, ejecting the companion. At a later time, the companion itself then explodes in a supernova. So putting all the elements together, you end up with a simulation of the production of runaway stars from the Large Magellanic Cloud over the last 2 billion years. This dashed line is the orbit of the LMC over that period. So you can see that basically all of them are staying in Large Magellanic Cloud. And that's what I was saying before. The binary supernova scenario can't kick stars. It doesn't often kick stars very fast. It's a few tenths of kilometers per second typically. But a large number are escaping here and here to form leading and trailing arms. And if you look at the leading arm, it stretches up into the region where we saw the hypervelocity stars before. And so if you compare to the hypervelocity stars, you can see that we can actually explain these hypervelocity stars using this method. And so the implication of this is that the reason no one's realized these stars are coming from the Large Magellanic Cloud before is that we've been looking in entirely the wrong place, almost perfectly the wrong place. It would be very easy for, if the Earth had a different orientation compared to the galaxy, this grey line could be a bit higher and we'd entirely miss these stars. So we're actually quite lucky we even found them at all. So the prediction is that there are 20 stars here and there will be thousands more in the southern skies. So when we know for sure, Gaia is carrying out an all-sky survey that will go deep enough to see these stars. And so according to my simulations, Gaia next year, in April 2018, should find 1,000 of these stars. It's for definite. If it doesn't see them, they don't exist. So watch this space. And going back to those stars which explode mid-flight, when a star explodes in a supernova, its core collapses into a neutron star black hole. And over 51% of the runaways did explode in a supernova, meaning that we get about 1 million neutron stars and black holes escaping the LMC. These dwarf the normal stars which got ejected, the hydrogen-burning normal stars I was talking about earlier. There's about 10,000 of those. And the only way you'll be able to even see them is if we catch a very young neutron star, which is called a pulsar, when it's really bright and still emitting radiation. And we might see about 2,000 of them. But that's a very speculative observation. So why is this actually interesting? Because I said before that all galaxies must have a fastest star. Why is it important that the Milky Way's fastest stars are coming from a different galaxy? So the first scenario is I'm entirely wrong. So there are no process that's kicking stars from the Large Magellanic Cloud. This would be an incredibly strong limit on what might be going on in this galaxy. It places an upper limit on how massive any black hole in the Large Magellanic Cloud can be, because if it was above a certain mass, it would have to be kicking out stars. And that would be much lower than the current upper limit. It'd be about 100,000 solar masses versus the 10 million limit we currently have. And that would tell us, that would be informative, because currently we don't actually know whether galaxies, the mass of the LMC, often host black holes. We know that very massive galaxies almost always do, like the Milky Way, but we have no idea about smaller mass galaxies, and that could be important on a more cosmological scale. That means that the binary stars, which I think are kicking out runaway stars, must not be kicking out runaway stars. And so they must be colliding or merging before the supernova occurs, which would tell us a lot about how binary stars work. Currently, you can't really describe our understanding as an understanding. There's a lot of holes there. It means that star clusters must be behaving very differently to how we think they do. It means the mystery of how stars remains open, which can only be a good thing. And scenario 2, I'm not wrong. So that means there's a stream of thousands of hyperstars stretching more than 100 degrees across the sky that I've managed to successfully predict. If there are any really quick ones, we can prove that there is a massive black hole in this galaxy, because we'll see lots of them streaming away from the center of that galaxy. If any are fast-spinning or chemically peculiar, that will be a sure sign that they've come from this binary supernova scenario. So that'll be able to learn about binary stars. You'll be able to tell when the LMC was forming stars by looking at where stars are spread along this leading arm, because it'll be composed of stars ejected at lots of different, along the entire 2 billion years of the LMC's past. And you'll also be able to figure out the mass and orbit of the LMC from the shape of this leading arm. So this question of whether the LMC is bound to our galaxy or is just flying past will be answered by these stars. So my conclusions, the fast stars in the Milky Way really could be on the run from our galaxy. It'd explain why we only see hyperstars in one part of the sky. It's actually quite hard to stop there being stars kicked from the Large Magellanic Cloud. I've based my models on our current best understanding of the physics involved, and all the assumptions need to be wrong in order for this not to work. It means that we haven't realized before now, because I'm looking at one half of the sky, the wrong half of the sky. And ESA's Gaia satellite will look at the whole sky in April 2018, so watch this space. Now, I did a press release for this work when I presented at a National Astronomy meeting in Hull in July. So this is a selection of the headlines. This is the Daily Mail's, which was surprisingly the best coverage, most accurate. Fast stars in the Milky Way that travel at speeds of up to 630 miles per second, maybe runways, other galaxies. That's all accurate. I mean, they converted kilometers per second to miles per second, which I suppose is more imperial. The Milky Way's fastest stars might be stolen was from the Atlantic in the US. I mean, these stars have traveled themselves from another galaxy. So it's like describing an immigrant as having been stolen from their host country. Stars might be galactic orphans. I mean, that's like you're assuming that a binary star is some sort of parental arrangement. Then red alert, high-speed alien fugitives are invading our Milky Way. Turbocharged solar runaways escape home galaxies, scream for cosmic backwater. I mean, you know that has to not be true, because in space, no one hears you scream. Yeah, any questions?